Hi again all. In this video I'll be discussing chapter 6 objective question from the guided tutorial module. Okay, so let's begin with question 1. So first question, which is correct statement for chemical equilibrium? So let's read all 4 statements before coming to conclusion, although there's already answers there. So the rate of forward reaction is equal to the rate of reverse reaction. That's true, we know that, but now let's read the next option. The total concentration of products equal to the of reaction. No, it not necessarily have to be equal. It just has to be constant when chemical equilibrium is achieved. Next, the rate constant of forward reaction equals to the rate constant of reverse reaction. No, if you see the forward reaction, let's say if it has a rate constant of K, the reverse reaction would have a rate constant of 1 over K. So that's wrong. Number 4, the product of equilibrium concentration of products and reactants equals to the Kc value. No, it's not the product between the concentration of product and reactant. It is actually a division product. Okay, you have to divide product concentration over reactant concentration. So the answer is clearly A. Now next question over here, it is asking you to calculate the equilibrium constant Kc, and they have given you the equilibrium concentration of the species involved. So first of all, make sure you write a correct equation for Kc and substitute in the corresponding values correctly, and you have an answer over here. Okay, 1.08 times 10 to the power of 7. I think I've missed out my 7 over here. Okay, right. Next question, question number 3. So according to the reaction of carbon dioxide and carbon which reached equilibrium, calculate the value of Kp. So here as we can see, there's solid, gases and gas again. So Kp, okay, would be only involving gases, right? So if I were to write the equation of Kp, we know that it only involves gases. Carbon solid is not involved. However, we don't have the partial pressures to fill this up, so this formula doesn't work. However, I want you to notice that a Kc value is given and temperature is given. Therefore, we can use the Kp equals to Kc RT delta N equation, substitute in the corresponding values, and delta N, how do we find? Number of mole gaseous product minus number of mole gaseous reactant, and we have the answer over here. So this requires you to substitute in the values correctly and press your calculator correctly and get the answer. Okay, so don't make careless mistakes, huh? Right. So question number 4 here. In which of the following equilibrium systems will the product concentration increase by using higher pressure? So remember, I told you when a system, when you increase the pressure in a system, you must remember that the position of equilibrium will shift to the side with less number of mole gases. Okay, so your job now is to predict where is the less number of mole gases, and by right that should be the product's side. Okay, because they want to increase the product concentration using high pressure. So we know that high pressure will shift the position of equilibrium to the side with less number of mole gases, and that side should be the product side. As we can see, I have labeled the number of mole gases for the reactant side and also the product side, and clearly for option D, we have got less number of mole gases on the product side. Therefore, D is the answer. Question number 5. Which of the following statement is correct about the reaction quotient and the equilibrium constant? Okay, so for the same reaction, Kc is larger than Qc. Okay, right. So this is a bit vague. I put a question mark there. For the same reaction, Qc and Kc have the same value. No, not necessary. Okay, and the reaction mixture whereby it is richer in products, Qc is smaller than Kc. No, when Qc is smaller than Kc, it's actually more reactant, not more products. So C is wrong. Next, the value of Qc would change until it reaches the value of Kc at equilibrium. Definitely. Okay, they will undergo shift whereby if Qc is lesser or even more than Kc, the shift, the progress will happen until Qc reaches Kc at equilibrium. Okay, question number 6. In Haber process, we have got equilibrium between all these three gases. Now what are the ideal conditions to maximize yield? Okay, so we want to increase the output of ammonia. What are the informations we have? We have got the forward reaction to be exothermic, and we know the number of mole of gaseous reactants and number of mole of gaseous product. So let's look at temperature first. So since the forward reaction is exothermic, okay, in order to maximize yield, we must push the position of equilibrium, we must shift the position of equilibrium to the right. So what favors exothermic direction? You have to reduce temperature. Remember that reducing temperature favors the exothermic direction. So cancel option B and D, definitely not the answer. Okay, so next thing we have to look at pressure. Now I have to shift my position of equilibrium to the right. Therefore, I'm shifting to the side with less number of mole gases. So what condition does the position of equilibrium move to the side with less number of mole gases? It's definitely at high pressure. So high pressure position of equilibrium moves to the side with less number of mole gases. You must remember that. Okay, so answer for question 6 is C. Now for question 7, okay, what do we have here is a sample of sodium hydrogen carbonate placed in an evacuated flask, and it's allowed to achieve equilibrium at 37K Kelvin. So what is the total pressure of gases at equilibrium? As you can see over here, whenever you need to know something at equilibrium and what is given to you is all initial conditions, you have to do the ice table. Okay, so in order to know the total pressure of gases at equilibrium, which are the products, as you can see over here, we have to find the partial pressure of their individual gases and add them up. So as you can see, I've clearly wrote the ice table. So since it is solid, it's not involved in the no values are involved in the ice table. So initial for products will be 0 unless stated. So in the case, this is all 0. And now we have got a change based on stoichiometry, and this would be the equilibrium pressure. Okay, so another one more information we have in this question is the value of Kp. So as we know, Kp for this particular reaction would be just the product of partial pressure of carbon dioxide multiplied by partial pressure of water gas. So getting the value of X here, which is 0.479, but what it is required is the total pressure. So total pressure means we must add both the partial pressures, and there you have it, answer D. Okay, right. So the next question here, they have given the initial mole of hydrogen and carbon dioxide, and they mentioned that 0.1 mole of carbon dioxide, yeah, correct. And they mentioned that at the end of the reaction where equilibrium was achieved, 0.1 mole of carbon dioxide was found, and you are required to calculate the Kc for the reaction. So let's begin with initial values. Okay, we can do a ice table with mole, no problem, although Kc requires us concentration, but later you can convert your number of mole to concentration by dividing number of mole with volume. So this is the respective changes, and this would be our equilibrium values. And we have an extra information saying that the equilibrium value for carbon dioxide with 0.1 mole, which brings X to have a value of 0.8. Right. So now that we have all the values of number of mole for all the reacting species, we have to find concentration. And if you look at the question, concentration is not given, therefore you can assume a concentration. So the best is to assume it's 1 liter, or you can even assume symbol V. Okay, why so? Because as you can see the working over here, Kc would be concentration of carbon monoxide multiplied by concentration of water divided by the concentration of hydrogen multiplied by concentration of carbon dioxide. And how do I find it? Number of mole divided by volume, and as you can see they get cancelled off. Okay, so if I were to just solve this, I would get my answer to be 2. So please take note of that. Alright, okay. Now let's go to question number 9. So question number 9, as we can see over here, they have given the Kp value for this reaction at two temperatures. Okay, so I can see that when the temperature is increasing, the Kp value increases. Okay, so when the temperature is increasing and the Kp value increases, that means we are producing more product. So if we are producing more product when the temperature is increasing, that means the forward reaction must be an endothermic reaction. So these are the things that you should be able to relate from your notes. Okay, I repeat, when you increase temperature and you see the Kp value increasing, that means more product is being formed. So an increase in temperature bringing more product formation, meaning the forward reaction is endothermic and the reverse reaction is exothermic. So is the forward reaction exothermic? No, that answer is wrong. More product is formed when temperature is increased. Yes, because you can see Kp value is increasing. And Kp depends on the amount of nitrogen used. No. Okay. And the value of Kp increases when the pressure is exerted on the system? No. We know that equilibrium constant only changes when temperature changes, not on concentration and not on pressure. Okay, so answer is boy. So question 10 over here, as we can see, which of the following statements are true regarding the equilibrium? So Kp value for the reverse reaction is this. I have checked it because Kp reverse will be 1 over Kp forward. So that's the answer, correct. Now when it's at equilibrium, the rates of forward reaction and reverse reaction are equal, same, yes, correct. Equilibrium shifts to the right when more NaCl3 is added. No, when more NCl3 is added, equilibrium actually shifts to the left. Okay, so option is just 1 and 2 correct. Alright, so question 11 now. So question 11, they are asking which of the following statements for the following reaction mixture is correct when the mixture is compressed. So remember, when someone is saying compressed, it means dimampatkan, and it's bringing about low volume, and low volume means high pressure. What do we know about high pressure? Position of equilibrium will shift to the side with less number of mole gases. So if you can see, all the species involved are gases, and you just calculate the number of moles, total number of moles of reactant, total number of moles product. So we can see that the system is definitely going to shift to the left. Okay, so when it's shifting to the left, less HCl is formed, correct, because more reactants will be formed. Okay, you have to, the HCl concentration will decrease. Now the rate of reverse reaction will increase. Yes, also because we are compressing the system, the mixture. The value of equilibrium constant will decrease. No, remember, equilibrium constant only depends on temperature. Changes in pressure does not change the equilibrium constant. So answer 1 and 2 only. So next question here, addition of ammonium hydrogen sulfide to the following equilibrium mixture. What's going to happen? Can you see ammonium hydrogen sulfide is a solid, so there's going to be no change in equilibrium concentration constant. Yes, correct. Increase in amount? No, it's not going to. Addition of solid is not going to increase or decrease anything. There's not going to be any shift in position of equilibrium. And net forward reaction? No. So answer is only 1. Alright. 13. For any reversible reaction, the value of equilibrium constant is affected by only the change in temperature, not the concentration, not the volume. And final question. A finely divided ion is used to catalyze the formation of Haber process. How does the ion affect the equilibrium? The ammonia will be produced at higher rate. Yes, addition of catalyst increases the rate of both forward and reverse reaction. So obviously ammonia is going to be produced at higher rate. More ammonia is produced? No. Okay, not more. Okay, catalyst will not increase the amount of products formed. And finally, the equilibrium constant, can it be increased, the value? No. Please remember, KCKP only changes with increase or decrease of temperature. Alright, and that's all for this video. Thank you.